Yeah, so do you have any questions about the previous times? Okay, so let's continue then. Uh, so, uh, mm, mm, and the last topic was homomorphic word identities. Uh, so we knew that there is some homomorphic symmetry, and if we make this symmetry non-homomorphic, then transformational direction is the following: plus g epsilon of z bar phi was the integral, well, actually with some coefficient which we will write later. It's just a matter of definition of conserved current. Plus the integral over d to z d bar epsilon j d bar epsilon j plus complex conjugate. And so we know this general formula, and now we want to take epsilon in some special form, namely, then we also studied the consequence of this transformation property for the path integral. Namely, we said that this path integral is invariant under the change of integration variable, and obtained the following equality, that sum of one z1 g epsilon of zk acting on O k of zk O Lugyan got how to write it better. Maybe better to write it like minus epsilon d bar j maybe. And we have chosen this epsilon, so epsilon of z bar. And we have chosen this epsilon such that it is homomorphic outside of this decays. So it is decay, and this domain is decay. So inside. Inside the union of decays, arbitrary in the complement. So if you have such property, So if you choose it this way, then we can get immediately that this correlator is a holomorphic. So let us write here Z. So taking into account this choice, we have that this correlator is holomorphic outside the decays. So the bar of this goes to 0 when Z is in C minus complement of decays. Right? Because epsilon is arbitrary, and we can choose it such that it is 0 everywhere and then 0 in some very small domain where it captures precisely the value of this d bar of j in that domain. Right? Or we can say that epsilon is a delta function located at some point, so all these terms vanish, and the only surviving term will be the bar of that correlator at one particular point. So. So it vanishes outside of that domains, and now we can choose. We can actually choose this epsilon to be 0 everywhere except some of these domains. Let us actually do this. So. 0 everywhere else. So in this case, we will have that this correlator O1 of Z1 G hat epsilon O k of the k On equals to the integral over a small domain of this object. But since epsilon is holomorphic there, we can write d2z integral of d bar, so integral over dk, d2z integral of d bar, epsilon of z, j of well, j of z, without specifying if it is holomorphic or not. Right? So we see that there is some equality which holds for any fields except for any fields added under this correlator together with this field OK. So this equality does not depend on all other fields except for this one. So we can say that we can say that it can be written not under the correlator, but as an operator equality, that g epsilon hat of OK of zk is the integral over dk minus due to that d bar epsilon j, oh sorry, without correlator, or OK of zk. So there is such operator equality. And now the last step, we see that as a function of z, this integral is integral of some derivative. So this d to z now can be written as probably I over 2 dz wedge dz bar. So it is minus I over 2. So it is dz bar d something. So we can write that it is d of so it's dz wedge d of epsilon j. OK of zk. Or in other words, it is what it is I over 2 integral d of epsilon j dz. OK. Zk. Well, actually, I will not care about this coefficient, and we will just insert an arbitrary factor of 2 pi, but we can do keep this signs current at least at this stage. So this is the integral of standard derivative of some one form. So it is I over 2 integral over the boundary of decay. Epsilon of z, j of z, dz, O k of zk. And actually, people choose different conventions in all these formulas when they work with CFT objects. So everything is renormalized by some factors of 2 pi. So we perform a change of normalization. And this homomorphic word identity looks like g epsilon hat acting on all k of zk will be 1 over 2 pi 1 over 2 pi I integral of dz epsilon of z j of z O k of zk. Integral around the point zk. So there is z, there is zk. So there is zk, sorry, there is z. And this equality holds for any function holomorphic at zk. So this holds for any epsilon of z. Uh, so are there any questions about this? So it's a kind of second part of this homomorphic word identities, and the first part is that d bar j of z ok of zk, so it is kind of second, and the first is that the boundary of z with OK of zk is holomorphic for z different from zk. Oh yes, yes. So and if you look at this, it is very natural to introduce the object which is called OP or operator product expansion. So in general, it will be defined for any fields, but here I will just demonstrate how it works for this OPs with symmetry current and some field. So in this example, we can say that j of z O of some set O of w equals to some j O with index k divided by let me think, by what precise power? Maybe just by z minus w to to the k. Hmm? Yes, precisely. So if some function is homomorphic outside the point, and so it means that we can expand it as a Laurent series. So and for now, let us write this like this. Probably I will not introduce, I will not write definition of term in the numerator because we'll think about this later. I want just to write some coefficients, ck of w divided by z minus w to the power k, and the sum goes from some from minus infinity to some n. So this Laurent expansion terminates at some point. Mm. Hmm? Uh, uh, because so we will think about this later, but there are always physical restrictions that dimensions of this fields should not be negative. Because but we can talk about this now actually. So let me think. Mm. So we know that correlator of fields of some dimension delta of z o delta of w is 1 over z minus w to power 2 delta, right? And mm, so if mm, it's a dimension in the sense that O delta of z times dz to power delta is an invariant object. So such field is a coefficient of form of weight delta. Yeah. So uh, Uh, and so since we have this um, behavior, it is natural to ask that in physical theories, this correlations should at least decay somehow. And so it imposes a restriction that delta should be positive. And but here if here dimensions of all these terms in this series should be the same, and dimension of 1 over z minus w to the k is k, so it means that dimension of ck is decaying with k. So if we go to two singular terms, we will get fields with negative dimensions. And this is the reason why this series terminates at some point, usually of not very high order. So is it an explanation? Okay. So, but in this case, we will be able to understand this. So, in this case, for some particular symmetries, we will be able to find all singular terms of this expansion, because this integral depends only on the singular term. So another way to write this OP is the following. People write sum from k equals to 1 to n, ck of w, z minus w to k, plus regular. So if you use this OP and substitute it into the homomorphic word identity, then we see that g hat epsilon of w is equal to 1 over 2 pi I integral dz. And let us substitute this. Epsilon of z plus, well, in principle, plus regular terms. But who can compute on this integral? So what will be the answer? Write one by one. Okay. Epsilon. That's all. No, why? It is some. No, it is epsilon. Yes, yes. So. K minus 1 maybe. Yes. Well, essentially the factorial from the Taylor series. Okay, and regular part does not affect this. So the consequences of this is that if you know transformation properties of O, then we automatically know a singular part of its OP within the current in J of Z. Oh, right? And another statement in that if you want to compute the correlator of this current in presence of fields with known transformation properties, we know singular behavior of this current around any of the points, so we can recover the function itself. We can say that we can write an explicit expression for the correlator with this current. Yeah. So, and let us study some examples. So the first is about this homomorphic translations. So the transformation is phi of z goes to phi of z plus a of z. And maybe plus epsilon of z, what is better? Let it be epsilon of z. And there is a field J, well, maybe with some coefficient. So there is field J of z, which is I d phi of z. Maybe we can put here minus I epsilon, something like this. And J of z, which is I d phi of z, so on this J of z transforms by plus d epsilon of z. And this field is basically the current corresponding to this transformation, as we already computed it. So the question is, what is the OP of J of z with J of z? So on one side we know that d epsilon of w. So on one side we have the epsilon of w, on the other side we have 1 over 2 pi I integral of dz epsilon of z, j of z, j of w. So what is the OP with, of j with itself? No. Mm-hmm. No, C1 is near epsilon. It's in d0 of epsilon. Mm-hmm. Mm-hmm. So, mm-hmm. Yes. Square plus regular. And this is the formula which we already saw, because J is I d phi, and correlator of phi was the logarithm. So it is a derivative of the logarithm in both variables. So first derivative of logarithm is 1 over z minus w, second derivative is 1 over z minus w squared. So far we obtained something unknown. Actually, I'm not sure about this sign in this symmetry. Maybe it's fine. Uh, but let us study another example. So, let me think. So, yes, so let us study another example. The alpha of phi, the alpha of z is e to the I alpha phi of z. So the alpha of z is multiplied by e to the alpha epsilon of z times e to the, so it's normally ordered or normalized. So the alpha of z. So what is g hat in this case? What in the action of g hat? Mm-hmm. Mm-hmm. So, and now let us write this homomorphic word identity. So, alpha epsilon v alpha of z, epsilon of z equals to 1 over 2 pi I integral dz j of z v alpha of w of w. Around w. So what can we say about the OP of G of Z with the alpha of W? Mm-hmm. Mm-hmm. Okay. So another OP. Uh, so and about this field, maybe it's everything we could say because uh, we actually don't know. No, we know some other operators like energy momentum tensor, but let us come back to this later. And now the illustration of how we can compute something. So we know such OPs, and now we want to compute some expression like J of Z, J of W, product of the alpha i's of the i's. By the way, here we can again see this global word identity, which corresponds to global transformations. So So let us consider the correlator identities. So suppose that there are some globally defined transformations. So we will say later what are possible examples of such transformations. But for example, for this shift, it's only epsilon equals to constant, because epsilon is a function and we want holomorphic function, and the only one function holomorphic on a sphere is constant. So, yes, of course, this epsilon defines some globally defined transformation, and then write, and then consider the correlator with J of Z. All let us consider the correlator of this kind: integral over dz, sum over all k's, integral around zk, so what can you say about such integral? So it's sum over integrals around all points, like the sphere, complex sphere or complex plane, and this integral is a sum of integrals around all points on this sphere. So can you say something about this? If epsilon defines some global transformation in the sense that it is at least so it is at least holomorphic outside these points. Mm. Hmm? No, but well, what do you mean? Yeah. Mm-hmm. So no, well, all the points are listed. So yes. So yes. So it is 0. Yeah. So and now we can use another part of the we can use the word identity itself. So at the same time, so it is 0, but at the same time it is sum over k and g hat epsilon acting on correlator O1 OZ1 g hat epsilon O k of zk. So it was or n of the n. So it is also 0. And in this in particular case, for example, we recover the condition that sum of alphas should be 0. Yeah, so let us see how this works in this particular example. So we want to compute the correlator g of z, v alpha 1 of z1, v alpha n of zn. So we know the asymptotics of J around any of this fields. And by the way, taking into account that J has dimension 1, let us multiply it by dz at the very beginning. So consider such one form. So it will equal to sum over all k's alpha k dz over z minus zk times the correlator. So it's in the answer. And so if we want to find the correlator itself, we should either know the OPs of this V's, or we can compute it from the path integral somehow. But here we can fix z dependence. And now this charge conservation condition, that sum of all alphas should be 0, appears when we look at this correlator at infinity. So when z goes to infinity, it behaves like sum of alpha k's dz over z. Like this. So if sum of alphas is not 0, it means that there is some field at infinity. Or we can take some fractional linear transformation and move infinity to some finite point to see that someone is sitting there. So, this is how this works. So it's kind of some almost trivial statement that so this statement about global transformations, it's almost trivial statement that germs of homomorphic function should glue to the globally defined function. So in particular, that sum of residues of some function is 0. So maybe that's all about this example. And let us look at the conformal transformations themselves. Yeah, let me check.
Sorry. You said 0 to infinity, and the conclusion is that if the sum of the alpha is not 0, there is some
yes, with this charge.
But the case is one of them.
Hmm? No, why? What is the problem? What is the problem? So we can just choose the local coordinate around infinity. Let us say that z is 1 over the infinity, and then this correlator in this coordinate, which is good at infinity, looks like minus sum of alpha k's d that infinity over that infinity v alpha 1 v alpha n. So uh, so this that infinity vanishes when z is equal to infinity. So it's some statement that infinity is the same point as any other point of CP1 with CP1. And if we so and we know that asymptotics of this one form is that j of z at any other point indicates presence of some vertex operators with charges alpha k. So this asymptotics was alpha k dz over z minus zk. So there were first order poles of this one form. And if we decide that we are so clever that we can put some fields with non-zero total charge and somehow violate this condition. So if we decided this, we should go to infinity and study what's going on there. Namely, we should go to the local coordinate where infinity is at 0, or maybe at some other point if you like it more, and look at the asymptotics of this dz j of z. So, and we see precisely the same kind of pole at this point with a coefficient that equals to minus sum of alpha k's. So even if you try to write some correlator with naively non-zero total charge, we realize that it is actually a correlator that has some field put to a infinite point. So we will see later how to do it technically, like how to place a field at infinity. But at least we see that if there is this behavior, if you have this behavior, then it actually means that we have not this correlator, but the correlator of this kind. So this V alpha 1, V alpha n should be replaced by V alpha 1 of Z1, V alpha n of Zn, V minus sum of alpha k's of infinity. So this is what we are actually computing here. And we just cannot write any meaningful formula for the correlator with a non-zero total charge, because we will violate the condition that sum of residues of one form on CP1 is 0. It is not physical, but a mathematical condition. So So the only way to do something with this condition is to say that this dz j of z is not one form, but some different object with some different transformation properties. But here we don't have a justification for such a modification because J was just I phi. So and phi was defined up to constant. So its transformation property was the transformation property of function. Okay. So let us study some other example. Namely, conformal transformations. So we have already seen that there are fields which have which behave like differential forms of weight delta. So and such fields with such transformation properties are called primary fields. So it's by definition such field is called primary. Primary of dimension delta. And let us see how they transform under the infinitesimal conformal transformations. So we want to pass from O delta of z times dz to power delta. So when we transform functions, we write something like this: that we define a new function of z, which will be a function of z plus epsilon, plus epsilon of z. It's for functions or for fields of dimension delta. But for some non-trivial field, we should write f tilde of z dz to power delta equals to f of z plus epsilon of z dz plus epsilon of z to power delta. And what will happen if we expand this up to the first power of epsilon? Mm-hmm. Let us maybe put this in the power delta as a row factor. So f of that plus what? Mm-hmm. Yes, and something else. Mm-hmm. But it was to the power of delta. Everything. Mm-hmm. Mm-hmm. Oh, plus of epsilon squared. And now we can cancel this delta and say that infinitesimal transformation, this g hat epsilon in this case is an epsilon of phi. Maybe let us call this f phi. Mm-hmm. So phi delta. That we don't forget what it is. So g epsilon phi delta equals to epsilon of w d phi delta of w plus delta d epsilon of w phi delta of w. Right? So, and the question: what is the current that corresponds to this transformation? So we want to write homomorphic word identity, and in the left-hand side, I write this infinitesimal transformation of the field, and in the right-hand side, it will be some integral around w, dz epsilon of z. So what should we put here? Hmm? No, what do you mean? No. The question is, what should be in the right-hand side of the Wick theorem? No, because what happened when we so where to write this? So, let me write it here. So there was this action d phi d bar phi, and we had to write here phi plus epsilon d defy epsilon with easy bar. Defy. And then expanded up to first order in epsilon and to find the term. So and show that it is so it is integral defy in the bar phi plus integral in the bar epsilon times something plus. But if you look at this integral, probably you can guess, for example, the power of this something in phi. What kind of term can we get in front of the bar epsilon? So it's phi squared. And it's called an energy momentum tensor. Namely, it's probably it's it is at z. So usually people call it just T of z. So it is T z. Maybe I will lose some factor, but this is the energy momentum tensor. And this is in any CFT, so it is just the definition that currents, conserved currents that correspond to conformal transformations are T of z and T bar of z. Energy momentum tensor and anti-homomorphic energy momentum tensor. So we put here T of z, which is this phi squared. And phi delta of w. So just by definition, energy momentum tensor corresponds to conformal transformations. And now, if you know this transformation, if you know this infinitesimal transformation property, can we compute the OP of energy momentum tensor with this field? So yes. Like this, and it is a generic phenomenon. Well, we obtained it as a generic phenomenon that if some field is transformed as a differential form of weight delta, then its OP with the energy momentum tensor has this form. And this allows us, in principle, to compute the OP of any. This allows us to compute the correlator of any number of fields with the energy momentum tensor. And let us actually do this, and let us also study this phenomenon. So we know that there are some global transformations. And those global transformations should impose some conditions of this kind. That sum of generators acting on the fields should be zero. Now, let us try to see such kind of conditions for conformal transformations. So the first question is, what is the number of global conformal transformations and how to write their infinitesimal form? Mhm. Mm, that why not C? So just so, global transformations. So to C, Z goes to A Z plus B over CZ plus C plus D. So determinant is 1, so it's something three-dimensional. And if you want to write vector fields that correspond to global transformations, then we can write the following submanifolds in this group. Like we can write that Z goes to Z plus A. This will correspond to vector field dz. You can write Z goes to e to the A Z. Actually, maybe let us obtain some vector fields with minus sign. So this is a vector field minus Z dz. And this is this mm, so there is transformation of this kind. It's called special conformal transformation. So this vector field will be minus Z squared dz. Right? So this is a this is a table of transformations, and about this table, I write epsilon z dz in this vector field, which corresponds to infinitesimal version of such transformations. So is it fine? And we can also we can also introduce some name for this vector fields. So we can define vector fields of the form minus L z n plus 1 dz. And so using this notation, it will be L0, it will be, L minus 1, L0, L1, such vector fields. And we can try to compute the commutator of such vector fields in general, and then see what it gives for these three vector fields that correspond to global conformal transformations. So who can tell what is the commutator of ln with ln? So we should take this vector field and differentiate z, which stands in the second one. So it will give a factor m plus 1. And then the opposite vector field act with it on z to power n plus 1. So it will be minus n minus 1. But no, wait. Let us let us say that these two minuses cancel, and then each derivative decreases the total power in power of z by 1. So it is z to n plus m, n plus m plus 1 times dz. So in terms of original vector fields, it is so it is n minus m times the n minus m times l n plus m, and this is called Witt algebra. Of course, or we can also say that this infinitesimal transformation, when z goes to z plus epsilon, corresponds to the vector field to the vector field. So epsilon of z corresponds to the vector field epsilon of z dz. Because vector fields are kind of classes of equivalents of curves that go through a point, and if you want to construct differential operator from this object, we just take we just differentiate in the direction of this curve. So. So yes, z of epsilon of z of f of z plus epsilon of z is f of z plus epsilon of z dz f of z. So this first term is in the vector field. In a sense, such shifts, such infinitesimal shifts, which can be shown really by vector field. So it is epsilon of z. They are in one-to-one correspondence. with first order differential operators. So, and here I computed the commutator of this field, and do you know what is the geometric meaning of the commutator of the vector fields? So there is, of course, algebraic definition of the commutator of the first order differential operators, but what does it mean geometrically? Uh, Fluxes, or how is it called? Flows, maybe. Fluxes. Ah, but and is it the same word for flux of the vector field on some surface? Yes, it's the same word. Flow and flux are the same word. Actually, in Ukrainian, in the same coincidence. And but if you want to see this, we can just we can just take Baker Hausdorff formula, like e to the tv, e to the su, e to the minus tv, e to minus su. Is e to ts commutator of v with u plus something. So in a sense, if we move first in this direction, then in this, or vice versa, then distance between these points will be precisely commutator of v and u. So yeah, so when we computed this commutator, we actually did the following. We say that there is a sphere without zero and infinity, so some kind of cylinder, and there are conformal transformations that map the cylinder to itself, maybe without preserving its boundaries. And some of these transformations are actually transformations of a sphere. So this transformation that corresponds to the global transformation of a sphere are this L minus 1, L0, and L1. And we can write the algebra satisfied by them. So L0 with L minus 1 will be L minus 1, L0 with L1 will be minus L1, and L1 was L minus 1 will be to L0. So, and this is called SO2, small SO2C, so the algebra of this vector fields. So mathematical notation for this is L0 is H, L minus 1 is F, L1 is well, maybe vice versa. L minus 1 is F, L1 is E. No. No, it is fine. Yes. because people study representation that are queued by EE, and it's the same as representation studied here, but it's not very important. Mm. And I propose to compute this commutator in this algebra of the vector fields because it will appear again. It will be one part of the Virasoro algebra. So we will see that in the quantum field theory, this algebra also exists, but it becomes centrally extended. And it is also a very typical situation that some infinite dimensional algebras which are well defined at the classical level are also well defined in the quantum theory, but obtain some trivial central extension because of the quantum corrections. And this is actually what I want to discuss next. In a sense, to see how to compute such OPs in quantum theory, and see, for example, what is the OP between T of z and J of z. This is probably clear because J is one form, so this will be just just this expansion for delta equals to 1. But what, for example, about the OP of T of z with T of z? So naively, T has two lower indices, so T of z dz squared should be invariant. But is it true or not? But before that, let us look at the restriction imposed by this field. So let us consider T of z in presence of some other fields. And let us multiply it by dz squared. Because in principle, at least if we care about the global transformations, which are just changes of coordinates, this should behave as two form. Because otherwise it will mean that we lose global conformal symmetry, and it is something quite bad. So let us, and we will actually see that it is true that these global conformal transformations are not affected. We will compute the transformation properties of T of z, which follow from its OP with itself. But let us study this later. We know that it has this OP around each point. So it will be a sum of all the differential operators, delta I over z minus zi plus squared dz. squared plus, or maybe dz squared overall, plus 1 over z minus di dzi. Acting on this calculator. So now I would like to play the same game, to go to infinity and see what happens there. If this object has some pole there or not. So we should say that z equals 1 over z infinity. And expand everything around the infinity. So this will equal to z infinity squared over z infinity to the fourth power. Acting on the calculator. So the first term which appears here, so in principle we have here 1 over the infinity fourth, but this is proportional to the infinity, this is proportional to the infinity squared, and well, let me rewrite it first in a more convenient way. We'll just set on the calculator. So we need to expand it around infinity now. In a sense, for the infinity equals to 0. And so the most singular term is in that last part. So it is 1 over the infinity cube, sum of di sum of dzi and acting on the correlator. Then a second term is 1 over the infinity squared. That contains sum of delta i's first, and second, we expand the denominator of that second expression. So it gives zi dzi. All right, acting on the correlator. So do you see it?
I don't see why the is the
Because how to get 1 over the infinity squared? So there is 1 over the infinity cubed, and we can expand this 1 over 1 minus the infinity zi at the infinity goes to 0. Hmm? Where?
I didn't see that in the first part we were missing
Oh, wait. We just expand it as a series in the infinity. So and the last term which we have here, which the last singular term. So there's also this the infinity squared everywhere. Over the infinity. So and what will we have from that last term?
just 1 over the delta 1 over delta infinity
Mm,
times
mm-hmm.
I.
Yes. Delta I is that I, right? But why minus? Mm. It's
Yes, plus.
mhm. Yes, it's geometric progression. Yes, acting on the same correlator. Plus O of 1. So if you say that nothing, that there is nothing at infinity, that all fields are in finite points, then there are three conditions. This equals to 0. This equals to 0. And this also equals to 0. Uh, right? So, uh, and we can also see that this corresponds to this G epsilons computed at this vector fields L minus 1, L0, and L1. So when epsilon is constant, we have just derivatives. when epsilon is proportional to z, we have delta. So derivative of epsilon is delta. It is here, and this one is zi dzi, and this is the same for vector field z squared dz. So this is a derivative of epsilon. This is epsilon dz, right? So in principle, we obtained what was expected. So. And what are the consequences of these three conditions? Yes, so there are three differential operators that kill correlators of primary fields, or at least fields that have this transformation property under the global conformal transformations. So we will see what is the difference, but let us say that such fields are called quasi-primary, if I remember correctly. So some fields that transform as differential forms of weight delta I under this global conformal transformations. So well, let us.
What the three constraints are is that the correlator needs to be conformal value.
Oh, so so it's a condition that holds in any conformal field theory.
Yes, but you see that these are the actions. Okay, it's not conformal value. The definition of the actions of zero minus one and two.
Yes, so it is so we had the statement that if there is some global transformation, then sum of g epsilons corresponding to this transformation acting on the correlator is zero. And here we obtained it in a little bit different way. So in some sense, so these conditions are equivalent to the statement that T of z as two differential, in the sense T of z dz squared, is regular at infinity. So, and there is no field there. Let us see what it gives us. So the very first question, if we consider a correlator of just one field, O delta of z, what does it equal to? So if delta is non-zero.
First of all, it doesn't depend on z.
Yes.
Then it is zero.
Yes. And let us look at another correlator. And delta 1 is different from delta 2. And let us look at the correlator O delta 1 of well, of 0, for example, or maybe z1. Well, z1 O delta 2 of z2. What can we say?
The first one is that it can depend on
Yes. And so on the second one, so from the second one, in principle, we can write that z z1 minus z2 times f prime of z1 minus z2 plus delta 1 plus oh, actually, maybe it's better to write two conditions. No, maybe it's fine. Delta 1 plus delta 2, f of z1 minus z2. And the third condition is z1 minus z2 times z1 plus z2 f prime of z1 minus z2. Right?
The minus before delta
But why? It is just sum. So now let us compute the difference of this object on for both expressions, like z1 minus z2 f prime of z1 minus z2 over f of z1 minus z2. So on one side it equals to minus delta 1, maybe minus this, it equals to delta 1 plus delta 2 plus delta 2 on one side. On the other side it equals to what? This expression 2 delta 1 z1 plus delta 2 z2 divided by z1 plus z2. All right. So and oh, is it okay? I just divided this by this, move to the left hand side and gotten this sum. And here I did the same, but moved z1 plus z2 to the right hand side. So if it is true, then what? Yes, of course. So it is clear that if we substitute delta 1 equals to delta 2, it will be just 2 delta, and this will be also 2 delta. And if they don't equal, it is well, it is clear that it is some linear equation on delta 1 and delta 2, and we already know one solution. So therefore, delta 1 should equal to delta 2. So and if they equal to if they equal, we know how to compute the square later from for example, well, we know it in general, but in particular we know it from this formula. It is some function. So this is a differential equation on f, which says that f is z1 minus z2 to power minus 2 delta. So O delta 1 of z O delta 2 of w, oh, maybe z1 z2. Actually, so in principle we can put some constant here, but since this is a bilinear form, and yeah, since it's a bilinear form, we can diagonalize on this. And since we can choose such bases in the space of fields that it is diagonal. Z1 minus Z2 to power 2 delta 1, for example. So, and the last question, so you see that if you have function of 3 variables and there are 3 of 2 variables and there are 3 differential operators that kill it, then this function exists only for some dimensions and it is fixed uniquely. But if you now have 3 variables and 3 constraints, these constraints will only fix the form of function up to the overall constant. And I actually don't know, I actually don't want to solve these constraints because we can try to guess corresponding expression, because we know that it is something, well, maybe let me erase this blackboard because it is some big expression. So we already have building blocks which are definitely invariant under global conformal transformations. It is this Bergman kernel, and we can try to construct a correlator from these Bergman kernels. So let us try to write that.
Like this, we used these 3 global transformation to fix the form of correlators up to 2, and then maybe we have some relation.
Yes.
But the other transformations.
No, but we are not. No, but
the one for the LN.
But they are not global transformations. So if you try to exponentiate such a vector field or look at its behavior at 0 or infinity, you will realize that it was not a one-to-one. So because so global transformations are transformations that map a sphere to itself one-to-one, and they so if it maps sphere one to one, it means that there is one preimage of infinity and one preimage of zero. But a preimage of infinity is a point in which a function has pole. Preimage of zero is a point where a function has zero. So a function has a single pole and single zero. And it is homomorphic everywhere else. And the pole should be of the first order because otherwise it will be not one-to-one immediately at this pole. So the function has a single pole, a single zero. So it is az plus b divided by cz plus d. So that's all. If you take any other function, it will map a sphere to itself n to 1. So, and if oh, and if you try to take some
But if I consider them locally,
but what kind of vector field can we take? Let us say that we have we have some vector field that has poles in the in the sphere. So let us say that epsilon is some a function alpha i's over z minus z i's. Example, let this pose be simple. And try to solve so the dtz equals to epsilon of z. Or maybe let us say that it has poles and it has zeros, and we know them. Sum of so sum of z minus ai over product of over z minus bi. Maybe to still be not very nice to integrate.
we take just one pole.
Oh, if it is one pole, then it will be one of so. No. Maybe it is fine. Yes. Yes. Let us take one pole. Yeah, it should be sufficient to see the problems. C minus zi, C minus a, z minus a. Oh, maybe you can even put a equals 0. It is easier. No, no. It can be. Yeah, this. So. Um, so a very nice conformal map, which is not one-to-one. So it's z of 0. So check what's in the recording. So let us see how it works. So when plus a plus a. So let us see how it works. So there is there is a real line, and we can go along this real line up to so it is z of 0, and here is z of t. Actually, we can map it in the opposite direction, probably. Yes, so there is a real line here, and we can go up to a. So, and in the image, it will also look like a piece of this real line from minus infinity to a. Then this term vanishes, and we can now go in the imaginary direction. So image of this point here will be a plus a minus square root of 2ct, or plus. Let me think. Oh, it's a square root of so the square root was negative, and it didn't cross 0, so it will be minus a square root of 2ct. So then, when this term vanishes, we can now go in the imaginary direction. So z of 0 can go to I to I square root of 2ct. Like this. And this will go on this plane. It will go to 0. So there is 0, and then we can go back. So it will be another piece of this line, and this is still at the point A. So no, it is A minus square root of 2ct. This is A. This is A plus 2 square root of 2ct. And then we go in a positive direction. So we obtain some conformal map which maps upper half plane without interval to just upper half plane. And you can imagine what it does with the whole complex plane. So it's clearly visible from here that it's not a single valued function. So it has branch cuts. And if you say that we work on the half plane, our CFT lives on the half plane, then we'll see that boundary of this half plane is changed. And actually, if we stick to the half plane, this symmetry group, this global symmetry group decreases. It becomes a SO2R instead of a SO2C. So it does not solve any problem. So is it kind of answer or not? And of course, if you take any arbitrary field, any arbitrary vector field will meet similar problems. Mm. Because they know theorem that only the vector, the only vector fields which correspond to one-to-one conformal maps are this. Okay, so are there any questions about anything else? Okay, maybe that's all. Thanks for your attention. And, see you the next week.